I think it should be recording. Yes, it should be recording. That's good. So the breakdown of this IQ is pretty much on one single method that we learn as integration by partial fraction decomposition. And I would like to clarify a bit super quickly about that thing before we begin. But after that, we'll talk about the differential equations. So this question here, b-balling, is a differential equation problem. So we're going to talk about both of these. So the course is kind of flowing in a way that you learn how to do integrals. And now once you have the knowledge on how to do integrals, you need to start to apply them. Okay, because usually in the previous course that you did in Math 104 or like the other ones, the differentiation part, just learning the method itself wasn't that bad. Okay, you had a bunch of rules, you learned them up, and then you start to apply them on optimization, related rates, and whatnot. So that's the general approach. But what we want to do here is for integrals, it takes a long time to learn how to do those and how to master these things, right? So that's why most of the course in the previous part is just about learning them. Now is the very first application that you learn is differential equations. So solving the equations that has differentials in there, like these ones. Oopsie, it should use the temporary pen instead of this one. So these ones are like differential equations. And to solve them, we need integrals on hand, okay? So we'll discuss how to do that. We're just gonna re-emphasize on converting this into an integral and then solving it. So knowing how to solve integrals is the very first thing you need to know. And overall, it's not a very bad IQ. Only this question is going to be a bit lengthy, but I think we will walk through this pretty quickly. Okay, so let's start with the very first one. Here, what they want you to do is to check whether you guys know how to decompose something given in this form. Okay, so two things before we even start. Partial fraction decomposition only works between rational expressions that have a numerator and a denominator that obey a specific relationship. The numerator must always be the degree less than or equals to that of the denominator. And if you're not sure what the degree of a polynomial is, you have to see what the largest power of x here is. So you see you have an x cubed here, you have an x, and you have another x here. So when you multiply it, you're going to end up with an overall degree 5 polynomial at the bottom. Okay, and on the top, you just have a constant, or in other words, you can say it's a degree 0 polynomial there. So this obeys the relationship that the numerator has a smaller degree than the denominator. Okay, so we can decompose it. And even before we start decomposing things, we need to make sure the denominator is in the perfect factored form out there. Okay, as factored as you can get it before you even begin. Okay, that's the few things you want to remember. So here you see this is not completely factored yet. So we'll have to take steps to factor it first and then do the partial fraction decomposition. So that's it. I'm going to refer to these notes that I posted before as well. These notes are there in the video that I talked about, and all of that stuff is already up there. This is just like general rules of how you break them down. So a thing to keep in mind is if you have factors here, the number of factors you have, like in this case, you have 2, you have 2 here too. You have 3 repeating factors of x plus a and an x plus b. So total 4 factors. So the number of factors you have will tell you how many decomposed terms you'll have in addition. So like in this case, you had 2 of those, you have 2 terms being decomposed. In this case, also have 2, you have 2 terms here. You have in total 4 factors, you're gonna have 4 decomposed terms for that one. So that's rule number 1. And the other thing is to decide what you should put in the numerator of each of these. Like in this case, you have a, but on the bottom, you have bx plus c for some reason. So how do you decide what's happening here? Is the degree of the numerator of individual decomposed fraction depends upon the relationship between the denominator and the numerator. So if the denominator of the decomposed part is a linear, the top has to be 1 less degree than that, okay? So that's why you have a constant on top, because 1 degree less than a linear is a 0 degree polynomial, that's a constant. Same thing here, you have x plus b, that's a linear factor. So on the top, you will have a constant term. However, in this case, where x squared plus b is a quadratic factor itself. So when you have x squared plus b a quadratic factor, the top has to be 1 less, so which means you have to have a linear. And to represent a linear term, like generically, you need to have a bx plus c, 2 terms, in order to represent that. And same thing goes for here. So that's just how you decide what's happening. Now, what you have to do for the factors that are repeating, like in this case, x plus 3 is repeating. So you have to write a pattern, okay? You'll be really good with these patterns once you learn how to do like sequence and series and expansions, but you guys are not doing that in this course. But the pattern here is follows like this. So the numerator depends upon what the factor itself is. In this case, it's x plus a. So it's a linear factor. It just happens to be repeating thrice. So for a linear factor, you know the numerator has to be a constant. So knowing that all of these things are going to have constants, the pattern is going to start off with just for writing the factor once, and then with b writing a factor twice, a squared, and with a c an x plus a to the cube, and that's how you expand a 3 times repeating factor. Okay, and then b by itself is just going to hang out by itself. So that's this. Again, I talk about this in detail in that video that I talk about on my channel with integration techniques. If you haven't watched that, you should watch it. But that's pretty much what we need to know before we start the IQ. So now let's go back there. Now in this case, we have to figure out what kind of factors we have and what are we dealing with. So I have a linear factor here. Okay. This is also a linear factor. And this happens to be a cubic. Okay, and we haven't talked about cubics technically, right? So what we can do is we can first of all break it down, because I can still factor it. It's not in the perfect factor form yet. You see there's an x that I can factor out of these. So I can factor out the x, and I can write it as x squared minus 4. Okay, so now I have a linear and a quadratic factor. Okay, so just to like on a bigger bird's eye view, you see how many factors? There are 4 factors here, out of which 3 are the linear ones, and there's 1 quadratic factor. Okay, now you can either treat this as quadratic factor, or you can further factor it down. You can further factor it down using this thing as x plus 2 and x minus 2. Okay, if you choose to do that, there's nothing wrong with it. It's completely fine to further factor it. But you can kind of use the leverage of having a quadratic factor as well, and you know how to do it. So it's completely your choice, whether you want to split it up again into like 5 linear factors, or you want to keep it as 3 linear and 1 quadratic factor. Okay, it's completely your choice. So if you keep it that way, the answer is still going to be the same. As long as you can show them the decomposition correctly, they'll give you the marks. There's no trouble there. Okay, so let's see. So now we have to decipher for the first part. Because we have x plus 2, 2x plus 3, and then x squared minus 4. So if I'm going to write both of them just in case you guys need more help with that. So I'm going to write should be 3 linear and 1 quadratic factor. Okay, if you keep it that way, you have to write it like this. So the 1 factor at the bottom is going to be x plus 2, and then plus, I'm not writing the numerators yet because I'll follow the rules later on. 2x plus 3 and divided by the x, and the last is going to be our quadratic factor of x squared minus 4. Okay, so we got all of them written down like this. Now we have to decide. None of the factors are repeating, so we don't have to do the pattern thing. So that's easy. Now the top has to be having a relationship with the numerator that has to be 1 degree or less. So since these are all the linear factors, so the tops are going to be constant. So A here, because A is taken to B here, the B is taken to C for that one. And we got to write a linear factor for this guy on the top. Okay, we have a quadratic on the bottom, so the top has to be a linear. So in that case, we'll have to represent the linear term with 2 unknowns, which will be dx plus E. So that's a completely fine way to expand it. Okay, that's one of the ways. But if you choose the other way to expand it into x plus 2 and x minus 2, then you'll notice that there's already an x plus 2 here. Okay, so the whole term in the expanded form, if you do it like this, with 5 linear factors, then you'll end up, so the term will look like this. I'm just going to try to write it out first. The x plus 2, the 2x plus 3, the x, and then x minus 2. And then the other x plus 2 will be multiplied by this x plus 2 to make it a square. Okay, a lot of you guys have already figured this out. So now in this case, we have total 5 factors, but 1 factor is repeating. Okay, the x plus 2 squared is repeating. So we can do it that way as well. The repeating factor needs to be dealt with, first of all, writing the first guy just by it is. Second time, you have to write the square. And you got to stop until you hit the power. So we hit the 2 power, we're going to stop there. That's how you deal with the repeating one. And then you're going to have a 2x plus 3. And then you have, not 1. Let me just try to get it out of the way. Over x. And then x minus 2. So now we got all of these factored out. The numerators depend upon what kind of factor you have at the bottom. So we have x plus 2, that's a linear. So on top, we have a 1 degree less, that's a constant. Same thing here. The factor inside here is a linear one. So the top has to be a constant, a linear factor. So a constant on top. X is also linear, so a constant on top. And x minus 2 is also linear, so a constant on top as well. Both of these decompositions are completely correct. Okay, there's nothing wrong with it. The placeholders for A, B, C, D, and E will change, but in an overall expression, you'll end up with the same thing. There's just 2 ways of decomposing it. Okay, so I hope this clarifies the very first problem. Any questions on this? If you wanna unmute your mic, please go ahead, do so. And if you want to chat, that's fine too. If I don't hear from anybody, I'll just go forward.
I just have a quick question.
Yep.
Sorry, can you hear me?
Yeah, for sure.
Okay. Does it matter what constant, like if A is over 2x plus 3 and B is over x plus 2, does it matter which
No, it
constant
doesn't matter.
is over?
Yeah,
Okay.
because those constants are A, B, C, D, and E are placeholders. So when you solve in real, right, the value that's supposed to be on top of 2x plus 3 will pop up there. So like if you choose B to be on top of 2x plus 3, so your B will take the value of what I chose as A if we happen to choose different ones. Okay, so it automatically kind of just work it out in a way that it just comes back together. Right now, there shouldn't be any difference. I can write it as like this if I want to. Shouldn't be any trouble there.
Okay, makes sense. Thank you.
Perfect. Any other questions? Okay, I hope everybody's good. Nice. So let's get started on the second one, where you got to go back and, do a lot of algebra. I'm just trying to get this out of the way so I can show you most of it on the top, and then we could just do the partial fraction expansion at the bottom. So here we have x cubed minus 1 whole squared. So you can follow your gut, and it can point you in 2 directions. Some people might want to expand the square first. Okay. Some people might want to just expand that. And some people might want to just want to expand the inside first and then square the later. Okay. Let's try to figure out both of them, right? Why not? Because we can take a leverage of this in order to make sense, because we know if this outer square is still sticking there, or we're not expanding it, we can still treat it as a repeating factor if the inside parts are nicely factored out, right? So let's do that. A lot of people might know this already, that the identity of a cubed minus b cubed is something, but I don't know that. So I'm just going to try to derive it, okay? And the reason why I want to derive it, because a lot of people might get confused with what other people are doing on the internet, trying to pull these identities out. So I'm going to write down here. What I know is how to expand a minus b whole cube, okay? Just for the sake of it. I know how to do that because I can write this as a minus b times a minus b whole squared. Then I can expand the a minus b whole squared with the squared identity. A minus b, a squared plus b squared minus 2ab. Okay, so we got that figured out. And then I can expand this further by multiplying the a minus b inside. So I'm going to multiply the a first. So I'm going to have a cubed plus ab squared minus 2a squared b. That's the first time when I multiply the a. And now I'm going to multiply the negative b inside. So I'm going to end up with a negative a squared b minus b cubed. And a negative times negative will give you a positive 2ab squared. Okay. So now it's time to just try to combine these terms up. So I'm going to write this a minus b whole cube here, because that's what we started off with. It's just going to be equals to, you have a cube and a minus b cube here. Out of that, on the top, you'll have a 3ab squared plus 2ab squared, so plus 3ab squared. And a minus 2a squared b minus a squared b, so minus 3a squared b. It looks weird. So now, because I wanted to isolate for a cube minus b cube, I'm going to move everything else on the left side, okay, and see what happens. If you isolate for a cube minus b cube, you'll be left with a minus b whole cube with a minus 3ab squared and a plus 3a squared b. Okay, that's what we're going to be left with. And now, out of these, if I factor, let me see, if I factor something out to make it look better. Out of this, I have a 3a. I can factor out a 3. And then in that case, I'll be left with, okay, a and a b. So let me try to factor a negative 3ab. So I'm going to have a minus b whole cube. And I factor out a negative 3ab from that. So the first time I'm going to be left with a b. And this I'm going to left with a negative a. Okay. And now, if I choose to put this negative back inside, so I'll have a positive here, and these will change places. The whole reason why I'm doing that, because I want to have a minus b as a factor term that I can factor out of the whole equation. So I can take this, and I can take that, I can factor out a negative a minus b from this. So factor a minus b from the whole thing, I'm going to be left with a minus b whole squared plus 3ab. And then you can expand that to be a squared. And I'm just going to continue here. A minus b. You have, going to have a squared plus b squared minus 2ab plus 3ab. So in essence, I'm going to be left with a minus b, a squared plus b squared, and this minus 2ab and plus 3ab will just give me ab. So this is pretty much the identity that you can Google up and find it out. And I'm going to write them down here so I can quickly use it because I've derived it already. The identity is going to be that a cubed minus b cubed is a minus b. Yep. Any questions?
Oh my God.
A lot of algebra, yes. Not minus, is plus, just. So we're not gonna worry about the derivation. You can probably start off from this point onwards. It's completely fine. But we're gonna keep that handy. And if you're trying to expand the x cubed minus 1, according to this, so.
Oh my God, rep.
You're gonna have that.
It's small.
See. I think it's Brianna whose mic's on.
Just have yours on top of your head.
Let me try to mute her.
Oh my God, rep.
Okay, we're back on it. So we have x cubed minus 1 cube, because 1 can be written as 1 cube. And that could be expanded into x minus 1, x squared plus 1 plus x. So that's the expansion of the inside part of the whole square. Okay, so now my term that I need to work with is x squared plus 5, 5x on the top, and you have x minus 1 with x squared plus 1 plus x whole squared. And now you can carry forward that square to both of these terms because they're being multiplied. So x minus 1 whole squared, and x squared plus x plus 1 whole squared. So now we got, in essence, 4 factors at the bottom in which x minus 1 is repeating twice, and x squared plus x plus 1 is also repeating twice. Okay, so now we're going to have expanded 4 forms, but one of the factors are going to be linears and the other one's going to be quadratics. So let's do that here. The expansion for the repeating factor x minus 2 will be x minus 2 plus x minus 1 plus x minus 1 squared. And for the other ones, it's going to be the same. We have x squared plus x plus 1, just like that. And then we're going to add x squared plus x plus 1 whole squared. That's how we deal with the repeating factors of twice. And now the numerators of each of these corresponding terms depends upon what you have at the bottom. We have a linear here, so it's a, linear here too, so b, quadratic here, so cx plus d, and a quadratic there too, and ex plus f. Okay, and does it make sense to kind of have it this way? If you think about it, well, in this form at the bottom, you have x cubed whole squared. So if you expand it out, eventually you're going to end up with a degree 6 polynomial, right? And a degree 6 polynomial could be broken down into 6 factors. And those 6 factors need 6 individual unknowns to deal with. And how many do we have? We have A, B, C, D, E, and F. That's how you kind of check your work, if it makes sense or not. Okay? This was kind of like a hideous algebraic thing to do, but we did it. Any questions on this now? Okay, I don't obviously expect you guys to just know right off the bat how to expand this guy. But the majority part is that this should make sense. The expansion and, you know, choosing the numerators depending upon what you have should make more sense than the other part. The top part is just algebra, which you can, you know, substitute by just remembering this, and that should be fine too. But all in all, it should make sense. Yeah, so the reason why we expanded it that way is because of my personal choice. There's nothing wrong or right in doing it that way, okay? Because I chose it to be in this form because I have seen that a cubed minus b cubed could be nicely expanded out because I know an identity, and then I can carry forward that square to that. However, when you have an x to the 6 in the bottom, the x to the 6 is going to be super hard to factor, okay? Because you need to kind of guess and eliminate and do long division there. And I'm pretty sure you don't want to do that. So just to keep it more straightforward with the identities and stuff, that's it. That's why I'm choosing this way. But going with x to the 6 just going to cause more work to do, and that's it. But it's going to be still the same thing. Okay, that clarifies the question. Yeah, no, but I didn't even know the a cubed minus b cubed formula at all. So I had to derive it in front of you to kind of just make it useful here. But I would say on the exam, these kind of expansions are very rare. They will never ask you to do a partial fraction expansion with 6 unknowns there, or like a cubic formula or whatnot. Okay, they will try to keep it very simple. So I would not worry too much about this on the exam, but it's just a good way to understand what's happening at the basic level. Yeah, that sorts out the first part of the first question. If we're all good, we should jump on the second one. Okay. I think we're good to go. Let's go. Okay, this problem here will take a bit of time, okay, to kind of understand again, because if you think about it, partial fraction decomposition is just algebra. We didn't even do any integration yet. The reason why we use the method, because it helps us to reduce our integrands to something that we know how to integrate, okay? Right now, I would never know how to integrate this function right off the bat, okay? So I need to figure it out into smaller fractions and then try to integrate it. So because here they're asking us for the integral, we got to do all the work. So let's get started. Here, you got to watch out that the numerator and the denominator are of the same degree. So there could be some rearrangements that you can do in order to make it more into the form where you have it less than the denominator, okay? You want to have the numerator's degree to be less than the denominator. So why don't we try to do some mental math? So here, some people might want to do long division, and that's completely okay. You can go ahead and do a long division of x4 plus 1 with x4 plus 3x squared. You can do that and you can get the same answer. No trouble at all. But I would want to make you more flexible with the work that you're doing in order to get you a better grasp of the concept, okay? So what I'm trying to do here, trying to get rid of this x to the 4 is going to be a difficult job if you don't have a 3x squared helping you on the top. Because if magically there was a 3x squared on the top helping you out, then you can just cancel both the factors if you can apply linearity to it. So I'll show you. So what I'll do is I'll rewrite the numerator like this. I have x to the 4. I'm going to add a 3x squared. I'm going to take away the same thing. I'm going to keep the plus 1 that was already there and divide it by this. There's nothing crazy I did here. Just added a 3x squared for my convenience. That's it. Now when I have it, I can split this through that position over there. So I can have x to the 4 plus 3x squared divided by x to the 4 plus 3x squared. And the rest of the stuff could be written as plus 1 minus 3x squared divided by x to the 4 plus 3x squared. So you can split up the numerators, keeping the denominator same down there. And this is where you can reduce it to be 1 because you have both the factors. So now the integral could be rewritten as 1 plus 1 minus 3x squared over x to the 4 plus 3x squared dx. So now this integral is composed of two things. One is just the constant 1 by itself. The other portion is something that you want to deal with. So I can break it down into two different integrals. So I'll have integral of 1 dx plus the integral of 1 minus x squared plus 3x squared. We got this. Now, this is easy because the answer to this one is just x. I'm going to write it down there. The integral of 1 is just x. So that's already sorted out. We don't care about it. The other portion is where you have it a perfect partial fraction situation there, where the denominator is more degree than the numerator, and you want to do the partial fraction expansion, and given that the denominator could be factored out. Okay. So what I can see here is I can factor an x squared from both of these. So I'm going to call this integral. Yeah. So you can do that the same question with the long division as well. So there shouldn't be any trouble in going through that way as well. So nothing crazy going on. I'm just doing it this way because I'm so used to not doing long divisions on the exam, just trying to manipulating the terms algebra, and that's it. So I'll mute the people who are actually making a bit of noise, but that's good. Now, okay, so I see something more. I still want to go ahead and without doing long division and kind of just, focus on the algebra part of it. So what I'm going to do is I'm going to factor the x squared at the bottom and rewrite this as, so I'm going to solve this. This is going to be x. I'm going to write the x here because it's already taken the integral off. And then I have an integral plus. I'm going to split these in two different terms. I'm going to have 1 over with the x squared factored out, this, and a minus 3x squared over factored out. So take a second and try to let it sink in what I did here. So I expanded, I split up the numerators on these while taking the x squared as a factor in the bottom as well, okay? Just like how we did it before. Any questions on this? I think this should be clear for everybody. Like this step right here that I did. I guess sometimes people do get confused with this kind of algebra. Okay, no questions? Okay, I guess we're all good. Awesome. So this is something that we got to deal with using partial fractions, but now I cannot reduce this anymore. However, this one, I could cancel the x squareds. And now I have it in form as reduced I can ever get. So this, the x that was carried forward from here, so I'm going to keep it, plus the, I'm going to write the easier integral first. 3 over x squared plus 3 dx. That's the first integral. I'm writing this one here. Okay. Of course, this is a minus sign, so I'm going to put a minus here. in front of that. That's it. And the last integral is 1 over x squared plus 3. So plus the integral of this. So now a lot of you guys already kind of know how to solve this one. Okay, you might want to go with trig substitution. Okay, why did you do that one first? Which one are you referring to, Hannah? Just trying to clarify. I just wrote them because personal preference, because that's an easier integral. That's why I wanna keep it in the level of increasing difficulty. It's just like a weird habit I have in my brain. So this is the easier one. That's the hardest one in the order. That's it. So just an order of writing them. Because here you can do trig substitution. You can get the answer right away. Okay, but I would hold on a bit before I do that, because I see x squared plus 3, and I know I'm gonna expand it into an x squared plus 3 as well, right? So I might see some algebra trying to cancel things up. So I don't want to do double work. So I would rather just kind of expand this first, reduce them to as easy as I can, and then try to do the integral later. Okay, so let's deal with this one first. I'm going to change colors. I'm going to call this an integral g for a second. Okay, just as a placeholder, I'm going to call that in, and I'm going to do partial fraction expansion on this side first, and then I'm going to carry forward down there. So we have 1 over x squared plus 3. So in total, how many factors do I have? I have 3. 3 factors in which x squared is repeating twice, and x squared plus 3 is just a quadratic factor by itself. So I have to expand them into 3 things. First, I'm going to write x, then I'm going to write x squared. That's how you deal with the repeating factors. And then the x squared plus 3 is just going to be x squared plus 3 because it's just a single factor. Now the numerators for this is going to be a, that's going to be a b, but for x squared plus 3, it's going to be cx plus d. Okay, so we're going to get this thing. Now, because we have that, we have to solve for a, b, c, and d, and that's where the trouble is. So let's try to expand it out. And if you guys know your way to solve this a, b, and c, d according to your equations, comparing the coefficients, or whatever method you like to use, please go ahead and do that. At the end, we're going to have the same answer. Okay, so as long as we can follow along, we're good. So what I'm going to do is I'm going to try to make this into a common numerator on this side with a common denominator. So I'm going to have 1 over x squared plus 3 on this side. On the other, because this a over x term is lacking 1x and 1 of the x squared plus 3. So we have a times x squared plus 3. The b term is only lacking an x squared plus 3. So that's this. The cx plus d term is lacking an x squared. So I'm going to have cx plus d lacking an x squared there. And at the bottom, you'll have x squared plus 3. So all I did is I took the LCM of all of these guys. Okay. So now if all of this is true, okay, then this equation must hold. The numerators must match up as well. Numerator on the left side is 1. On the right side, the numerator is ax, x squared plus 3 plus b, x squared plus 3 plus c, x plus d times x squared. Okay, so the reason why I want to use comparing the coefficient method is because most of you guys have learned that. So I'll try to do that method here by combining all the terms. So if you expand it, you're going to have ax cubed, and then you have ax plus that, so 3ax. You're going to have a bx squared plus 3b, and on that side, you're going to have plus cx cubed plus dx squared. Okay, so now I'm going to combine all the like terms and factor out the common x powers from it. So 1 here sticks like that. Out of the ax cube and the cx cube, if I factor out the x cube, I'm going to be left with a plus c. Out of the bx squared and the dx squared, if I factor out the x squared, I'm going to be left with b plus d. And then from there, out of the only x term that I have is 3ax. So I'm going to have 3a. And the only constant I have here is 3b. Okay, So the 3b here will just be left by itself. So now here you got a bunch of information trying to come up straight up here because comparing the coefficients. So now because on the left side there's no x cubed term, okay, then the first equation you can make is that 0 must be equals to a plus c. Okay, that's the very first one because there's no x cubed on the left. The second equation is comparing the x squared because there's no x squared on the left. Then you have an equation saying 0 must be equals to b plus d. Okay. The third term is comparing the x terms. So because there's no x term over there, that tells us the third equation is going to be 0 equals to the coefficient here is 3a. And the constant that we have, the fourth equation, is 1 on the left side. And on the right side, the constant is 3b. So we have these equations in front of us. We can use these to figure out a, b, c, and d. So right off the bat here, you can see b is just equals to 1/3. Okay, because if you use the fourth equation to isolate for b, you're going to get b equals to 1/3. From this equation, you can automatically conclude that a needs to be 0. Okay. From this equation, you can conclude that d is just equals to negative b. And because you know b is 1/3, then you can say d is negative 1/3. That's that. And then because on the top equation, you have a plus c being equals to 0, because a is 0, that tells you that c must be 0 too. Okay, so now I have all my constants up here. So I have a equals to 0, b equals to 1/3, c equals to 0, d equals to negative 1/3. So now we can write our expanded form according to this expression here. And let's write it out. So my expanded form, because it's going to be 0 over x plus 1/3 x squared, because you remember the b is in the x squared, so it has to be there. C is 0, so you're left with only d, and d is negative 1/3, so negative 1/3 over x squared plus 3. And this could be simplified into like the easiest form to be plus, let me just try it, 1, 3x squared, and negative 1 over 3 times x squared plus 3. That's the expanded form. So now, any questions about the partial fraction expansion just by itself? Like how I did it, what's going on? So how do you know which constant should be cross multiplied to? You mean while taking the LCM, or you mean while comparing the coefficients? Like, are you talking about in this part, or how do I get this? The second one. So you mean this one, right? How do I get this one? Okay. The reason why you do that is you have to see, you want to make the same denominator on each of these terms. So a over x already has an x. Okay. To make it have an x squared times x squared plus 3 in the bottom, you need to multiply this by an x. So you have top to multiply with the x. And then you need to multiply with x squared plus 3. So the top has to multiply with x squared plus 3. So that's how you figure it out, because you have to see which factor is each one of them lacking in order to make them have the same denominator. So a over x was lacking an x and an x squared plus 3. However, the b over x squared was lacking only x squared plus 3, because it only needs an x squared plus 3. Because if it has that, then it matches up this form, right? On this side, x squared plus 3 only lacks an x squared. That's why you have an x squared being multiplied there. Okay, so just gotta pick one that is missing from each one of those. Usually, what you're accustomed to is just trying to cross multiply it and call it a day, right? But that's not how sometimes it works. It's always better to kind of like see it as a place where you need to fill in the gaps with what's missing for each one of these factors. Okay, does that kind of clarify what's happening? Okay, perfect. So we got that. Any more questions about partial fraction expansion? I guess everybody's good. Cool. So we got that. Now I'm going to try to write this as one single integral here. So we're going to replace that here with the integrals. That is x already taken care of, plus negative 3 over x squared plus 3's integral dx. The expanded form could be written as separate integrals. So the first thing is going to be 1 over 3x squared. So I'm going to add an integral of 1 over 3x squared. And then we have an integral of minus 1/3 of x squared plus 3. Okay. So now we have two integrals that have x squared plus 3. One being this one, and there's one more here. So you practically have a negative 3 times the integral of x squared plus 3, and you're subtracting 1/3 of x squared plus 3 from it. So you have negative 3 minus 1/3 of the integral of x squared plus 3. Right? That's pretty much it. Because if you pull the constant out, that's what you're going to end up with. And this expression could be kind of reduced to be negative 10 over 3. Any questions about this thing? I'm trying to combine these two integrals because they both have the same stuff inside it, and it's just different constants. So why don't I reduce them using the constant algebra to make it into one single integral, right? That's what I did. Hopefully no questions on this, right? Okay, we're good. So that's how I'm going to write it. So this could be reduced further into x plus, I'm going to write minus 10/3. Why don't I have a plus there? X squared plus 3 dx. And the lonely integral of 1 over 3x squared is just going to hang out by itself. Cool. So now we have reduced it into those easiest forms that we recognize how to solve. The integral of 1/3 x squared, I'm going to leave it up to you because I like to give you these little DIYs for yourself to, you know, enhance your concept. This is going to be done by power rule. And the integral for this one is just going to be 1/3 is going to be pulled outside. This. Okay, that's the integral for that. So now, so far, I have already solved for 2 of these. So minus 1 over 3x. The only integral that's left is a negative 10/3, 1 over x squared plus 3. Okay, and this takes you to the land of the trig substitution. Some people might know the answer right away, but I'm gonna, just for the sake of it, I'm gonna perform tricks up here so you guys can follow along. Here we have a x squared plus 3, okay? When you have an x squared plus some constant, you wanna make sure you have an x squared plus 1 there, because then when making a substitution of tan, you're gonna end up with this. So now if you want clarification on this, I can go back to my notes that I use usually for all of these. So when you see an x squared plus a squared, in this case, a is just, a squared is 3. So a is square root of 3, because here we have x squared plus 3. So if you write this as in that form, you can write it as square root of 3 whole squared. So a is square root of 3. So go back to the notes. When you see that thing, you want to substitute x as a tan t, and then substitute dx with that, whatever a you have, a secant squared t dt, and then the expression that you have x squared plus a squared will become a squared secant squared t. Okay, that's just one single line to follow along these stuff. So let's try to do that here together. When we have x squared plus 3, so in this case, my a is square root of 3. Okay, that's just following my method. Those notes, I'll post it up in the group as well. They should be up somewhere on the videos in the descriptions, but I'll just, cut the fuss and I'll just post them again for you guys. So you can refer to this PDF. So a here is square root of 3, and they're telling us to substitute x as square root of 3 tan t. So from there, dx will just be square root of 3 secant square t dt. Okay. Now we gotta sub all of these back in, and because we know, because of when you substitute this guy here, your expression as per the notes, because I've already derived it for you, this x squared plus a squared, the thing that you started off with, will become just a squared secant square t. So we're gonna end up with that. So here we have x minus 1 over 3x minus 10 over 3. So now the integral, we have the dx turning into that. So we have square root of 3 secant squared t dt. The bottom expression of x squared plus a squared will just become a squared secant squared. So a squared is going to be 3 secant squared t dt. Okay, that's how you follow the notes if you want to do that way. But if you want to follow the basic approach, the very trivial one, you got to watch the video that I post about trig sub. I talk about why we do the substitution the way we do it, the intuitions and why they always work that way, just to kind of put you back on the track. So that's this. You got to figure out the secant squared cancels out. Why do I have a dt there? My bad. Shouldn't be dt at the bottom. That cancels out. So we have basically x minus 1, 3x minus 10 over 3, the integral. So square root of 3 divided by 3 will just give you 1 over square root of 3 dt. And the integral of this will just give you x minus 1 over 3x, that's the old stuff, minus 10 over 3 square root of 3 times t. And now because I want to convert, so where did you get the square root 3 from? The square root of 3 is trying to compare these forms. If you see back here, I have to make it into x squared plus a squared form. Okay, right now I have x squared plus 3. I can write this as x squared plus, so that it resembles x squared plus a squared form. So from that, you can say that a is just square root of 3. Does that make sense? And then that square root of 3 just ends up here, and then eventually does the algebra to make 1 over square root of 3 at the bottom. Okay, so we got that t here. Now we got to substitute for t. So in this case, if you chose x to be that way, you got to isolate for t. So you have to send the square root of 3 on the right side. Will just be equals to tan t. And from there, if you isolate for tan, you're going to get, if you isolate for t, you get t equals to the arctan or tan inverse of x over square root of 3. So that's what the t value is. So when you plug it back in all, you get x minus 1 over 3x minus 10 over 3 square root of 3 times tan inverse, of course, a plus c at the end for that. And that's how you solve this question. A lot of weird stuff happening here. You have to do partial fractions. You have to do trig sub. You have to be very good at algebra, trying to figure out things and manipulate them. It's just a very wholesome question. But hopefully it makes sense. Any questions about this? Hopefully not, right? I'm still waiting. If you guys have any questions, don't hesitate. Just put them up there. Okay, I hope everybody's good. Yep, scroll up. Yeah. I'm going to post this PDF as well, so don't worry about it. You're going to get all of these. It's just that my work is going to be all over the place. So to navigate through what I wrote and why I wrote that, it will be handy to see the video first and then try to follow along with it. Because just reading the PDF might confuse people. So that's how you solve the question. And if you know this a little hack that I'm going to show you now. So if you go back, I'll post these notes later as well. On the end of these notes, you'll see this. So these integral shortcuts is just trying to help you out in an exam situation. So if you think about an exam question, I personally think that IQ question will be a bit too much for an exam because it tests you on a lot of things. So it's going to either take up 2 integral questions into one single example to be tested on the exam. So they won't kind of like go all over the place with that one. It's just too much work. Yeah, so these integral shortcuts will help you straight up because here, if you compare to this form, what we had was 1 over x squared plus 3. So if you can identify what a is, a, in this case, we compare that, is just going to be square root of 3, just like how we did. You can straight up jump to the answer. That integral, the answer to that integral will just be 1 over square root of 3 tan inverse of x over square root of 3 plus C. Because all you got to do is you have to identify what A is. You have to know which one of these rules you're going to use, and then plug in the A accordingly into that place, and that's it. And that's pretty much what we did in that question. In this question, our answer for this one was 1 over square root of 3, this guy here, tan inverse x over 3. So if you don't want to do trig sub, or actually you can't avoid it because on the exam they might expect you to do it. So you can do the trig substitution, but at the same time you can remember these forms. You are all science students. There's a lot of stuff you got to memorize in biology. So I'm pretty confident that you're sure, you know, you can remember these things if you practice a bit. Just try to take a post-its and post them anywhere on the fridge or somewhere. I think you should show your work for the IQ specifically. I think you should show the work because let's be honest, you had a week to complete this, so they might expect you to kind of write it out all in the long way instead of just using the shortcut. So I would recommend trying to knowing the work, but this is very handy for the exams. Okay, if you're tripping during the exam, what's happening, you can definitely know these things, and if you're running out of time, you can write this thing and just hope for the best, right? Sometimes this can save lives. So try to memorize this. This will be helpful, and that sums up the first question of the IQ. Very lengthy, very long, but we got it done. Let's go to the application one, the b-balling. So I would feel like that I'm hosting a National Geographic Channel show if I try to talk about this because it's just too much words, but I'm going to summarize this in a very short form. So what we're trying to talk about here is how bees hunt down wasps. Okay, bees just trying to, you know, not embrace social distancing and trying to just capture the wasp in it, and then they raise the temperature by isolating the wasp inside that place and to a certain temperature that the bees can survive but the wasp cannot. Okay, somehow the wasp hasn't, you know, mutated biologically to survive up to that temperature where the bees are, so this works out for them. That's how they hunt the wasp. So now what they do is following a mathematical phenomena of Newton's law of cooling. Okay, and Newton's law of cooling has a standard differential equation, looks like this. That's just pretty much how it is. And now what they want you to do is that suppose that a wasp, so the wasp dies, and the bees dies at 49 degrees Celsius, but the wasp dies at 47 degrees Celsius. So what they want to do is they want to start off at the initial temperature of 20 degrees, like the ambient temperature, and then they're going to circle up the wasp, and then they're going to raise its temperature from 20 all the way up to 47. Okay, all the way up to 47, and the 47 is the spot where they're going to, you know, kill the wasp. But here, what they want to do here is a constant, and the ambient temperature in this case is 48. That's what they want to reach up to, the difference between that place. So you got to see how it flows. The temperature at the initial spot was 20, and we got to reach up the ambient here of 48 degrees Celsius. So how will this work out? You don't know an equation that tells you what's the temperature of the wasp at this time, okay? But you want to find that function out, given that if obeys this differential equation, okay? That's very important to kind of remember. The capital T here determines the temperature, the small t is the time. So you're going to look for a function which is a function of temperature as time progresses. So you need that thing. That's what you're looking for. How we solve that? They want to use the method of variables, separation of variables, to solve this initial value problem. And if you want to be like motivated towards why you need to know this, why this separation of variables is important, I can take you back. I can take you back to my collection of stuff so I can show you what's happening. So this, in the last term, for the final that you guys had, not this one, this one. So here is a differential equation that you have. It looks pretty nasty. It's a differential equation between a function of time, a p, which is a function of time, and you got to solve it. In your final answer, you don't have to isolate for p or t, but you have to solve this differential equation. And it looks pretty daunting here, right off the bat. But this was on the exam. So differential equations will definitely have a question on the exam. So you need to know how to solve these or be really good at them. That's why I want to just give you a motivation towards these. And now let's get back to the previous ones. Where did it go? here. Now, how do you solve a variable separable problem is to move the variables on one side. For the capital T, you want to move all the capital T things on the left, and you want to move the dt with the t's on the right, small t's, okay? So here, when you have it in this form, you can write, you can cross multiply with dt on both sides. So you're gonna have capital DT equals to K. So remember here, K and TA are two constants, where capital T is the only variable of the function. Now we have this. Okay, I moved the dt over to the right side, and now I'm going to move these on the bottom, on the numerator. So I'm going to have dt ta minus t equals to k small dt. So this is the process of separating variables, so that the capital T variables are with the capital dt differential, okay? And the small t variables are with the small t differential. On that, in this case, we don't have a t, so we have just k on this side. So we got to this form, and then we can do is integrate these. So we're going to integrate both the sides here. So integrating that will require you to do use substitution here, okay, for that thing. So remember, TA is just a constant, so don't worry about it. If you want to substitute TA as 48 right away, you can do it. But I tend to keep it that way until the very end, so I can show you a general way of solving this differential equation. And then you can replace it with whatever TA they give you in the exam. But now you can choose to either substitute 48 right away in TA and then treat it as 48 minus T at the bottom, or just kind of see it as a constant. Okay, so let's try to see that. So I'm going to keep it, again, DIY for you. So you guys should be able to solve this. The integral of that is going to be ln, minus ln of TA minus t. And on the right side, the integral of k times dt is just going to be kt. Okay. Now, once you have done the integration, you kind of know the whole solution is done. So both the integrals will have a plus c. What you can do is you can have a plus c on the right side because it's just arbitrary constant. So you can keep it on either one of the sides. That's fine. From here, you have to isolate, okay, for capital T. So when you do that, you get capital T. So I'm going to try to write the steps here because I would want you guys to know how to do that. What you have to do is, first of all, move the negative on this side. That's the very first step. When you move the negative on this side, then to get rid of the ln, you got to take the exponential to both sides. Okay, so you're ending up with this guy. So you have TA minus t, that's the inside part, because you take the exponential, with the exponential of negative kt plus c. And now you might question, why didn't the plus c have a negative there? It doesn't matter because it's a constant. You can have a positive, negative, whatever you want. Okay? It doesn't make a difference. That's this. So now from here, you can isolate for capital T. It's just going to be TA minus e to the power negative kt plus c. Okay, so we got that. Now, to make it look a bit nicer, you can use exponential rules to kind of make it in this form. Capital T is a constant, minus e to the negative kt times e to the power of c. You can break it down using the exponential rules. When you have kt plus c on the top, you can write it as e to the negative kt times e to the c. So we did that. That's how it's done. That's already good. I can call e to the power c because it's going to be a constant, because c is a constant. I'm going to call e to the power c at some
take a photo quickly.
some initial value.
Any phone.
We got this capital C. I'm going to call that again. So now my whole expression, you can call it anything. You can call it F, call it P, whatever you want to do it, but I'm just going to call it capital C all over again. Minus capital C e to the power negative kt. So that's how we solve this thing. So now the things that we know about this equation are going to be good. We're going to put it inside here. So here, what we know is that the ambient temperature is TA, that's 48. So that's going to be 48. I don't know what C is, but we can solve for C given the initial condition. We know the initial condition is this. So what if we found an equation to our differential equation, a solution, and the solution must obey this condition too. Solution must say the initial temperature was 20. Okay, initially the wasp was at a temperature of 20. So if you want to do that, what I can say, I'm going to write it first like this, e to the power negative kt. So we know t of 0 is 20. Keeping that in mind, so you have 20 here on this side with a 48 on that side, minus c e to the power negative k times 0. Okay, I'm going to zoom out a bit. This, and then e to the power 0 is just kind of what you're going to get here. So from there, you can say c is nothing but 48 minus 20, which is just 28. So the final equation that you have to submit here as a solution for this will be that capital T as a function of t is just going to be this 48 minus the c value is 28 e to the power of negative k t. So there's still one unknown there, okay? Because they said your solution will involve a k because we don't have enough information yet to solve for the k value, so I'm going to keep it there. And that's the answer for the very first one. It's an exponentially decaying function, okay? That's just how it works. But because of what we're trying to mimic here is heating up, it will be an increasing function, not a decay, because it's going to heat up from starting from temperature 20 all the way up to 48. Okay, so we're going to have this exponential here. That's the solution to this one. Any questions about this method? Or any bits and pieces?
No. Sweet. I love it.
No questions? Okay, cool. That's the solution to that equation. Now, what we have to see is kind of just to have an intuition of this. I'm going to try to put that on Desmos and try to see what happens, okay? So that you guys can figure out what this looks like. So because Desmos doesn't take t as variable, I'm going to use x. So I'm going to use capital T of x being equals to, the function was 48 minus 28 e to the power of some negative k. I'm going to have a minus there. The k, and because instead of small t, I'm going to use x because that's the variable that it takes. So I'm going to add a slider for k. And now this is how it looks like. So now, because the time only starts at 0, so this only makes sense if you're starting between 0. So I'm going to put that restriction on domain in Desmos. So for x greater than 0, I think I gotta get rid of this. Yeah. So that's how it looks like. And you guys can see, because the initial temperature was 20, that's where we begin at. And we're going to try to heat it up. That's how it heats up. It's an exponential kind of increasing function where it heats up the thing, and that's where it's stable at. Stable value is 48 because the 48 is the temperature where they want to go. They don't want to be anywhere away from that. So far this function looks good. And let's see if we change the k values, how it changes. So the k value kind of determines how fast the temperature rises. See that? So remember, we can only have k that's positive because the convention is already having a negative there. So I'm going to have a value of 0 to, let's say, 100. So I can move them around. So if the k is very, very fast, if they heat it up very fast, so you see it's a very sharp spike. But if the k is very small, you see it gradually heats up. So that's the whole way to kind of visualize what k is. So now we're going to solve that, given some more information. So here, they know after 1 minute, the wasp's temperature is 32 degrees Celsius. So they know. So it started at 0. So the initial temperature was 20 degrees. And then now, after 1 minute, so t of 1, it's 32. So the wasp is heating up at that rate. Now that we know these 2 points, we can actually solve for k. So if you plug in that value into the function, we know the function is just 48 minus 28 e to the power negative k t. So t of 1 is 32. Knowing this, you can have 32 on this side. And then 48 minus 28 e to the power negative k times t. T is 1. So this. From there, what you can do is you can isolate for e to the power of minus k. So I can send the 48 to the left, so of negative 32 minus 48 equals to negative 28 e to the power negative k. And then you can divide the both sides by negative 28. So you have 32 minus 48 divided by negative 28 equals to e to the power minus k. And to isolate for k, now you got to take the ln of both sides. So when you take the ln of both sides, you're going to have ln of 32 minus 48 divided by negative 28 equals to minus k. So k is nothing but negative ln of 32 minus 48 divided by negative 28. So you can go ahead and solve it into like actual numbers, but I'm just going to keep it this way, okay, because of the algebra and all that stuff. Of course, I can solve 32 minus 48 should be negative 16. Yeah. So k is negative ln of negative 16 divided by negative 28 is going to give you just 16 by 28. And they could be further factored out. Because 5 is that's a 7 and 4. So it's minus ln of 4 divided by 7. I guess, right? I think. Yeah, I'm pretty sure. So that's this. Now that my k value is this, let's try to see if our Desmos kind of agrees to what we're trying to solve. So I can manually put the k value here to be minus ln of 4 divided by 7. And according to this, I should have a temperature of 32 when x is equals to 1. When x equals to 1, I draw that line. The intersection is at the y point 32. So far, our functions are agreeing to what the thing we're modeling. Okay? Does it make sense? Any questions on how we solve for k? So the k in numerical value 0.5596, all that stuff that you see from Desmos, but you can keep it that way. Negative ln 4 over 7. Right? Any questions about this? About the work that we did? Nope, right? Okay, pretty good. We're all on the same page. Now we got to determine how long will it take for the wasp to die. So we know the wasp will die. Oops, I went all the way back. We know the wasp will die if we are at 47 degrees Celsius. So let's see. We want to make it to 47 degrees Celsius. So why don't we check it here? If my y is equals to 47 degrees Celsius, and that should happen at a time of 5.954. As you can see, the intersection point is right there, right? So after 5.954 minutes, the wasp should be dead, okay? And let's see if you get the same results from actually solving it manually, right? Let's try to check. So we're trying to find when this dies. So we have to see, we have the temperature equation. The reason why I'm not gonna write this ugly k in the equation, because I just don't want it to be messy. I will substitute for the k at the very end. So I'm gonna keep the k in the equation just for the sake of solving it. And then at the end, I'm gonna plug in the value that we found. So here we have 48 minus 28 e to the power of minus kt. That's the temperature. And now we want the temperature to be 47 degrees Celsius. So we need to figure out what time it's going to be 47. So I'm going to equate it to 47 and solve for t. So minus 28 e to the power negative kt. Move the 48 over to the left side. You have 47 minus 48. That's negative 1 equals to negative 28 e to the power negative kt. So now divide both sides by negative 28. You're going to have 1 over 28 e to the power negative kt. And now to isolate for t, you got to take ln of both sides. So you're going to get ln of 1 over 28 equals to negative kt. So the t from here is just equal to ln of 1 by 28 divided by negative k. Okay, and negative k itself Okay, the reason why 47 came on that side is because we want to find the time when the temperature is 47, because the wasp dies when you have it at 47 degrees Celsius, right? So now I know the capital T temperature, but I want to solve for small t. Like what time does it become 47? So that's why I equate the left side of the equation as 47 and solve, right? That's this. And then the minus k, the k value is that. So if you plug it in, you get t ln of 1 over 28 minus of ln 4 over 7. So all in all, you're going to have an ugly expression, ln 1 over 28 divided by ln 4 over 7. And that's the time. Okay? That's the time why we're going to work on this. And then the 47 is given here. The wasp will die if they reach a temperature of 47 degrees Celsius. That's why we use 47 there. Okay? Perfect. So now we got this expression. Let's see if it works out or not. Let's try to plug it in here to see what the value is for that. We're expecting it to be somewhere like 5 minutes, almost 6 minutes. 28, that's this. And now that should be divided by the ln of 4 divided by 7. And that's exactly what we're expecting. The time came out to be 5.9. No, there shouldn't be negative. No, the k is minus ln, but because you have a minus already there because of this whole thing, then minus of minus will become positive ln. That's why. Okay, makes sense? And now everything's in the agreement. We were expecting it at 5.954 and we got the exact same answer. And that's how we model the murder of a wasp. You can make a Netflix series out of this, but that's pretty much it for summing up this IQ. So now, any questions about this IQ in all together? The units needs to be in minutes because the whole situation is talking about minutes, right? And that's a very good question. Should be 5.95 minutes. I should write that here probably. Yes, thanks so much for that. And yeah, any more questions on the whole thing or the IQ or whatever? And any questions apart from IQ as well? I'm pretty okay to answer that. I took up more than an hour, and I'm sorry for that, but it's just I wanted to be more detailed in my solution and stuff, so that's why I wanted to take more time to kind of go over this. Yeah, if you have any questions, please ask me. If you're not, you feel free to go. Yep, you guys are very welcome. Okay, I'm gonna hang out here for reading out your kind wishes and just some questions if you have any. Yeah, so Zoom meeting about like in our midterm part, I will definitely try to host one that's also on the cards, but I'll update that up in a bit. And you briefly explain how you got the coefficient Q1. Didn't understand the class notes. Oh, so the coefficients in this one or the one part after that? Okay, this one here. So A, B, C, D, and why did I have A, B, C, D there? Is that the question? Like, okay, how do you find A, B, and C? Is going to involve in finding equations. Okay, and that the idea is behind you equating. Yeah, the second part is where we actually find them. So here, what we say is if we try to expand this, we're trying to equate this equation to the expanded form. Okay, if the expanded form matches up, then the condensed form should also match up. So what I do is I reverse engineer this. I reverse this back to a condensed form like this, where all of them have the same denominator. And I take the LCM of the whole situation, and I get this on the top. These are the things that we get on the top with the corresponding expansion and the denominator. So now if we're saying the expanded forms are same, the condensed forms need to be the same as well. And following that same ideology, that if you made the denominators equal, then you are forcing the numerators to be equal as well. So here, the numerator on the left side of the equation is 1. The numerator on the right side of the equation is all of that mumbo jumbo you have. Now we got to solve for A, B, and C that makes this whole thing come together. Okay, so when you have it in this form, what you're trying to do is you're trying to expand this whole thing from the traditional method that you learn in the book. The traditional method is to expand it all and have them in the most expanded forms and like terms collected. And by that, I mean I'm going to expand it here. So this is ax cubed, 3ax, I have an x squared term, I have a b, I have this and that. So we got all these terms here, and I'm going to combine the like terms. So I'm going to start out with the biggest power of x first. In this case, I have an x cubed, and then I have an x cubed here too. So I have an ax cubed plus cx cubed, and if you factor out the x cubed from them, you're going to be left with a plus c. So the x cubed term on the right side has a coefficient a plus c. Okay, and now on the right side, you also have x squared terms. You have a bx squared, you have a you have a dx squared too. So bx squared and dx squared, when you factor out the x squared from them and combine them, you're going to have x squared with a b plus d. Okay, so the coefficient of x squared on the right side is b plus d. And when you think about the coefficient of x, that's just going to be 3a. So that's why I have it written like this, x times 3a. And the only left constant is 3b. So we're going to have that lonely over there. Now, if you're saying the two equations on the left and the right are the same, while the corresponding coefficients for the x to the 3, x squared, x, and the constant should be same too. Okay. Now, since on the left side of the equation, there is no x cubed term. Okay. So whatever this a plus c is must be 0 in order to make them equal, right? Make this, the right side have no x cubed term as well. So that's where you have the first equation here, where a plus c is equals 0 because you don't have any x cubed term there. Now, you don't even have an x squared term. So that enforces the b plus d, whatever that is, needs to be 0 as well. That's why you get the second equation from. And then once you have the second equation, then you look on the left side, you don't even have an x term. So the coefficient of x must also be 0. So that tells you that 3a must be 0. However, the constant on the left and the constant on the right do match up. So constant on the left is 1. The constant on the right is 3b. So that 1 must be equal to 3b. That's how we get a set of 4 equations, and we have 4 unknowns to solve for: a, b, c, and d. Right? And we got that thing. That the zeros were there because there are no terms on the left side to match up with them. If you had like x cubed plus 1, then this first equation a plus c will have 1 because the coefficient of x cubed on the left side is 1. Okay, and that's how it will start off with that thing. Okay. That makes sense, right? Cool. So that's question answered. Any more questions? No problem. Yes, you guys also have a great day. Enjoy the rest of your Sunday. If you guys have no more questions, you can feel free to leave the meeting, and I'll leave when everybody's gone.
I do have one
Yep.
question regarding, if you could just recap. See. Part B of question 1.
Part B of question 1, yes.
Yes. When it comes to starting to integrate or using trig functions to help answer the problem, could you distinguish again between the shortcut and then how you think they want us to solve for this particular IQ?
So the method of shortcut usually just works with just basic, memorization. And the reason why the shortcut works is because it has been done with the same way you should technically do for the trig sub questions. But instead of a constant, you have an a. Okay. So let's say you had like a weird constant. I'm just gonna add a sheet at the very end of this. So I'm gonna try to explain that to you. So now, like the question was asking you to solve this integral, right? 1 over x squared plus 3. So you can do trig substitute for this particular question. But what I did to come up with the shortcuts is just replace that 3 with some constant, okay? So replace this x squared with an a squared here, okay? And solve for that general expression to just develop a shortcut. So the way you should do that here is because you see an x squared plus a squared form, you want to make sure you are able to convert it into a tan, because you know the prerequisite that we have here, that tan squared t plus 1 is going to be condensed into secant squared t. So I want to make sure I convert that thing there. In order to have it in that form, I need to convert it into this using a substitution. So I'm going to substitute x as a tan t. When I do that, the reason why I do that, you'll see that when I plug it in there, your expression is going to be a squared tan squared t because of the x squared, and a plus a squared here too, out of which you can factor out an a squared, and you'll be left with tan squared plus 1. And that tan squared plus 1, because of this rule, is just secant squared. So you'll have 1 over a squared secant squared t. And that's the whole idea behind what we do. And now let's see, if we do that substitution, what happens to the dx? We have to kind of substitute for that too, right? So if you take the derivative of this side with respect to x, you're going to have 1 equals to a times derivative of tan t with respect to x is going to be done by implicit derivative. So derivative of tan t is going to be secant square t times dt by dx. And if you send the dx on this side, you have dx equals to a secant square t dt. So now instead of this ds, I'm going to plug those in. So we're going to have a secant square dt, a secant square t dt, a secant square t dt. So now you see right out of the bat, you can cancel the secant squareds because that's what it reduced out to be. The a's with the cancel with the a squared. So you'll just have 1 over a dt as the integral. And the integral of that is just going to be 1 over a times t plus c, of course. And what was t to begin with? T came out from this guy. So I'm going to try to isolate for t. I'm going to move the a on this side. So x over a equals to tan t. So from there, t must be equals to tan inverse of x over a. So when you plug it back in, you get 1 over a tan inverse of x over a plus c. So that's the generic shortcut method for doing all that work, which came out because of trig substitution that we did. Okay. So technically on the exam, when they only give you a question about trig substitution, you should be doing all of this work. You should be manually picking up a function. Like in this case, we picked up a tan t. So in this case, you will pick up x to be square root of 3 tan t. And then go on with the whole process, okay? Instead of a's, you'll have square root of 3's and all that stuff that's popping up over there. But that's just the whole way it should be done. On the reason why we have a shortcut there is to help you remember the form correctly. Just in case if they give you, there's a possibility of you being an online exam and, they just ask you the answer for this integral. So why don't you just use the shortcut and get the answer right away instead of doing the long method and save yourself some time for the exam, right? So that's the whole motivation behind having a shortcut. Because if, God forbid, and you can't complete your exam in some time, or something goes wrong, or what happens and all that stuff, you can definitely use a shortcut to jump up to the place and actually finish off the question. Because you see, in most of the question, trig sub is just a part of the bigger picture, like in this IQ as well, right? So the shortcut just helps you out, but by the book, this is the whole method that you should always do, the trig substitution method. And again, I talk in more detail about that in the video. If you can't find it, just let me know and I'll send it over to you. Hopefully that clarifies.
Great, thank you very much.
Yeah,
makes more sense.
Yeah. And I had a question in 2A, where did the ln came in? So 2A, we're trying to figure out, it's in the same document. Go back. So you're talking about, where's the ln in 2A? Oh, my bad, 2A, it's right here. Okay. So the reason why you got a ln here is you would do u substitution. You'll say u equals to ta minus t, and then du equals to minus dt. And when you substitute it in there, you'll get an integral of negative du divided by u, which happens to be negative ln of absolute value of u. When you plug in the u back, you're going to get this. Got it? Yes. The minus sign is because of the u substitution. So, well, technically it was supposed to be done by you, but you got me. Any more questions? Why the minus dt? Because derivative of capital T with respect to t is just going to be -1. That's why you have a -1 there. And I just kind of like do that, start off from the back. You should be technically doing it this way. So the derivative of this side with respect to capital T is going to be du by capital dt equals to derivative of ta is going to be 0 because it's a constant. And derivative of minus capital T with respect to capital T is going to be -1. And then you move the dt on the right side to make it look like this. I'm just lazy because I keep on going through these fast. And you'll be at the same point as well sometime. But does that make sense? Hopefully that clarifies it, right? So the capital T's temperature, should it be 0 as well? No, because they said the ambient temperature of the surrounding, where we started off, is 20. Okay, so it's given here. So they're telling you that this is 0. So you must start it to be at 0. As 20 degrees Celsius. This is the variable inside, right? So this is T. Oh, I mean, you're talking about, my bad. You're talking about the derivative, right? Okay, my bad. Du over, so we're taking the derivative with respect to capital T, or with respect to temperature, okay, of this expression. So that's why you will have a capital D capital T over there. So capital T's derivative with respect to capital T is just -1. It shouldn't be 0. Does that clarify it? I guess. Yeah, because we got to substitute for capital DT, right? So we have to take the derivative in with respect to capital T. And with respect to capital T, derivative of minus capital T is just -1. That's it for that one. No problem. Any more questions? If you guys don't have any questions, feel free to leave the meeting. I'm going to be waiting until everybody's gone. If you have any other questions that you want to ask, you can ask them too. Stop recording now.